Welcome back. In this video, we're going to look at some of the models, the fundamental models that show up in Chapter 2 for first-order differential equations. I'm going to start off with probably the most important, most famous one is that, and that is the exponential model for growth or decay. We think of this as a population, then we relate the change in that population to some multiple of the population, which says that if the population is small, it grows slowly. If the population is large, it grows faster. And the larger the population, the faster it grows. This kind of model works well for a population that is uninhibited. There is nothing restraining its growth. You can think of this related to things like bacteria and, to some extent, small like insects and other small animals that can abundantly grow very quickly and fill a space where they're not competing with other animals. So this is the basic exponential model. I mentioned that it's growth or decay. This exponential model also works to describe the nuclear reactions that involve isotopes that reduce down after a certain amount of time, that have a certain half-life, isotopes that decay. For example, with radioactive isotopes, they are unstable, so they only last for a certain amount of time, and the number of those isotopes left over after a length of time called a half-life is half of the original population. So this rate will relate that half-life depending upon what information we have for the initial condition and the time. So this model is very important. We see it pop up a lot. It's very simple to solve also. It's separable and linear. And if you haven't seen this one a few times, you can actually write down the answer really very quickly. It's simply some constant multiple of e to the RT. That's the exponential solution. That's why it's called an exponential growth, is that the solution is an exponential. This is the most fundamental solution to a differential equation. We'll see it pop up a lot. But we're not going to talk about the solutions right now. We just want to talk about the different models and how they show up. So the next step on improving the exponential models to be more realistic for a general population is to add a restriction on that growth. We call this the logistic growth model, where the derivative is equal to a multiple of the population times 1 minus p over n. So this second component will drive the rate towards 0 when p approaches n, when p, the population, approaches the carrying capacity. So in both cases, we have the exponential growth rate, which is how it grows, how the population grows at the beginning, exponential growth curve. And then we have the carrying capacity. And this is the ideal value of the population, the amount of population that P will converge towards if it's below, and converge towards if it's above. It's difficult to think about a population as above a carrying capacity, but if the carrying capacity is suddenly lowered, there's been some examples like if you have a closed system, like an island, and there's a fire that wipes out part of the forest, that quickly reduces the carrying capacity of the animals on that island, and they will converge down towards that ideal carrying capacity. Okay, So that's our logistic growth model. It is nonlinear because of the extra term, but it is separable. See the video on solving that. And it actually is an almost linear or Bernoulli model. So it can be solved in one of those two different ways. The next step up from this is the harvested logistic growth. And this is often used by the Fish and Game to determine how many tags to determine when they're tracking the number of tags for fishing or hunting. So a harvested population is something like a food source, like deer or fish, other things that are being relied upon. Now you may think that deer aren't necessarily a food source because people eat other things. It's true, but they are being harvested. Their population is being harvested. So this amount H tells us a certain constant decrease in that population. And the other part is simply the standard logistic growth rate. Now what this minus H does, we see in the bifurcation analysis of section 2.7. And it'll lower the ideal the actual ideal limiting value of P away from N down further and further and further based upon how big H is. And there's a point where H can be too big to have any roots of this polynomial. Now, if we look at this in terms of P, it's a quadratic, which will have two different roots. But under certain conditions, that quadratic may not have any real roots. And that's the point where the population is over-harvested. And that's what we see in section 2.7 in analyzing the bifurcation analysis for this population growth. Okay, so those three are all built upon this exponential model, all based upon population growth dynamics. And we'll see more population growth dynamics come up when we have two populations that feed off of one another. Either one's a predator, one's a prey, or they're competing against each other. And we'll see that in linear differential equation systems. But now I want to show you one more model that's similar to this, and this is Newton's law of cooling. Now, Newton's law of cooling is very similar mathematically to the exponential growth because it has a linear term, not a quadratic. It can be solved as separable because it's autonomous. This A and K are parameters. Or it can be solved as linear because this is just a linear multiple of T and this is a constant. I'll put that up there, harvesting rate. Here we have the outside, usually the air temperature, and on the bottom we have the rate of heat conduction. Thermal conductivity is the term we use for that. So this goes into thermodynamics. And what it says is that the rate of change in the temperature, or you could use this to quantify heat energy, but temperature is a way of simplifying that. The change in the temperature is proportional to the difference between the outside temperature around a certain body and the temperature inside that body. One quick example of that is a cup of coffee or tea. In this case, it's tea. Got a little tea bag. So this tea had water that was initially at boiling and has been rapidly cooling down. Why is it cooling down? Well, because the air around it is much cooler. So we have air at a lower value, the outside temperature of the air, the temperature of the T at a higher value, mostly water, and when we take the difference here, we get a negative value. The conductivity, rate of heat conduction between the water and the air is going to be a positive quantity here, relates how rapidly the heat will transfer. But we can easily see that this A minus T will give us a negative. Air temperature is less than the temperature of the water, which means the temperature of the T, water, will decrease. The rate of change is negative. That's why we often will call it the Newton's law of cooling. But this law also works with heating things up. Let's say we pull an ice cube out. I don't know why I would. I put an ice cube in my tea. Could cool it off quickly, right? Now I can treat the ice cube as the internal temperature I'm tracking and the A, or outside temperature, as the temperature of the water that it's in. And then the transfer rate between water in liquid form and water in solid form would be my heat, my thermal conductivity. In that case, the temperature of the ice will increase. Now, not necessarily through Newton's law of cooling, because when you go from ice solid to water liquid, we actually go through a phase change. So there's some energy transfer that's need to be built into this model. So this model does not have the built-in energy required to move between phases, the phase transition energy. But as long as we're not changing phases, as long as we're not going from solid to liquid, this is a pretty good model to represent it. And sometimes you'll see this model used with a tongue-in-cheek style, to represent the cooling of a dead body, to try to figure out in a murder mystery style when the person actually died based upon the time when the body is found. So oftentimes we play some games in not just solving this equation, but also playing around with finding times in the past when things happen, not just in the future. So it's kind of an interesting model. Mathematically, very similar, exponential form. Physically, it represents something very different. Instead of population, talking about the temperature or the heat change, and we often will play around with different initial conditions, moving backwards in time versus forward in time. So, interesting model. First physical law we're going to look at is the mass balance law. This one is stated fairly simply at the beginning, but of course it's vague and we need to fill in the details. So the rate of change in quantity, we can think of this as a derivative, is equal to the input change minus the output change. And the example where we saw this in chapter 2 is in the single compartment mixing problem. In that case, our input is represented as a flow rate in times a concentration in minus a flow rate out times a concentration out. And we often will think of this compartment as something like this Z shape, where it's a well-mixed liquid in the middle, We have an inflow coming in, outflow going out, and the inflow is known. So our flow rate in and our concentration in are known quantities, but our flow rate out is unknown because our amount inside is unknown. And so the rate of change of the amount of material inside this tank that's being mixed changes based upon a constant or a known input, but an unknown output related to the amount X. Because the concentration out is going to be the amount X on the inside divided by the volume. And then the flow rate can be controlled. So that is a single compartment mixing problem. Notice that the unknown variable X shows up in a linear term. Volume is going to be changing with time, but not changing with concentration X. So this mixing problem, though a little bit complicated in its formation, is linear. It's always linear. The key discrepancy here is whether or not this volume is a constant or is a changing function of t. If it's a changing function of t, the integration by parts piece needed may be a little tricky. So, another linear model based upon a general law of input minus output seems very simple, but then gets broken down into components and then fleshed out into some pieces. And again, there's also a video on this mixing problem for you to watch a full example run out. Now let's look at the other main law that shows up in chapter 2 and also shows up in future chapters. That is Newton's second law of motion. And this is MA equals the sum of the forces F. You can think of this as F equals MA, but there's often more than one force. So MA is equal to the sum of the forces. An example we have from chapter 2 was the parachutist problem. We have some parachutists falling down. They have their parachute open, thankfully, and the force of gravity is pulling them down. But the drag force on their chute is pulling them back up. So we can represent this either as a first order differential equation or second order, which we'll get to later. So let's start with the first order form. We have the mass of the entire object, parachutist and parachute, times the acceleration, which I'll write as dv dt, the change in the velocity. And then the force of gravity pulling down, as long as they're not falling from too great of a height, is simply m times g. If you want to think of it in terms of the parachutist perspective of the ground crushing up at them, minus the force of drag, which would be some multiple related to the area of the chute and the strength of it, times the velocity raised to some power. And depending upon the speed, this power can be between 1 and 2 often. When p is 1, we have a nice linear differential equation. When p is 2, or any other number than 1, it's nonlinear and is a little tricky to solve. But there's an example in section 2.5 where we look at doing a substitution that then turns this into a Bernoulli equation and can be solved from there. But more importantly, this right-hand side is always autonomous. There's no t that shows up, which means it can always be analyzed using a phase line or stability analysis to determine what velocity the parachutist is converging towards as they fall. We call that velocity the terminal velocity. So that's an example where we can solve it. It's ugly, but we can solve it. More importantly, we can analyze it very quickly without solving it to give us some of the more important information, like knowing what the terminal velocity will be based upon the different components of our parachute and the model we're using for it. This p-value is usually determined experimentally based upon different data sets, but usually is found between 1 and 2. Okay. So that covers up the fundamental models from Chapter 2 that describe all first-order differential equations. There are lots of other differential equation models, most of which are built upon these styles. I'll give one shout out to the project at the end of Chapter 2. It's the project from the book at the end of Chapter 2, and that's for the single neuron equation. And that builds upon the idea of the logistic growth to have a sigmoidal curve to it, but uses that solution to form the slope of a new differential equation. So take a look at that if you want to look at some of the biological applications. Many of the biological applications are built upon some of these more physical or mechanical models. Okay, that wraps up our overview of the models using first-order differential equations.